Hello, and welcome to MSA Prep for 5th grade Science. I'm Scott Hange from the Howard B. Owen Science Center, and today we're going to be focusing on one of the standards of science, and that would be the 5th standard, which is physics. Let's take a look at how that is written out in our state guidelines. Students will use scientific skills and processes to explain the interaction of matter and energy and the energy transformations that occur. So what we're going to do is to take a look at some sample problems. These are public release items that are found on the internet, and this particular one deals with the concept of freefall. Now, as you know, whenever you see a reading, you catch your breath, you don't get upset, and you look at the questions that follow. If you notice at the top of this page, it indicates use the passage below to answer numbers 1 through 3. So it means there are 3 questions related to this reading. So let's take a look at the questions. Here's question number 1. It's written, which graph best shows the motion of a car in a free fall ride as a car drops? Now, it's very important whenever you look at a problem like this that you look at these, which are called the axes. You have a vertical axis and a horizontal axis. Each one of those on a science graph should be labeled. In this case, this is height in meters going vertically, and going horizontally across is time in seconds. So as you go further out this way, the number of seconds gets larger, and as you go in this direction, the number of meters gets larger. So you have 4 different graphs to look at. Okay, let's take a look at the next question. This question is written, the seats in a car of a free fall ride are replaced with heavier seats. This change requires A, more force to lift the car, B, less time to stop the car, C, a lower rate of speed, or D, a higher rate of speed. And finally, the third question, which is a BCR, is written as follows. 2 different shaped objects, and that's very important, and we'll talk about that later. 2 different shaped objects were dropped from the same height. Data from the investigation was recorded as shown below. And you have a data table here. You have the object shape. These are called headings, and they're very important. Object shape, mass in grams, height dropped in meters, and average time to fall in seconds. Then you would be asked in this question to explain why the average times to fall were different for the 2 objects. In your explanation, be sure to include, first, the errors in this investigation, or could occur in this investigation, how these errors affected the outcome, and how the investigation should be improved to obtain valid data. Now, what I'd like to do before we get to the reading is to do a very brief demonstration. I have a highlighter and a battery. The battery is much heavier than the pen or the highlighter. So on the count of 3, I'll drop this, and you try to figure out, make a hypothesis, which you think will hit the table first, the heavier battery or the lighter highlighter pen. 1, 2, 3. Looks like they hit at the same time, but in science we need to do a bunch of trials, so let's try another time doing this, another trial. 1, 2, 3. Looks like the same result. Let's try it one more time for a third trial. 1, 2, 3. Looks like the same result. Now that may surprise some of you. However, what I was showing you is an example of an object in free fall. It's dropped and gravity is acting on it. You may have experienced this if you're brave enough to go on a roller coaster. You're going on the roller coaster and you hear the clickety-clack sometimes of the chain as it's pulling you up to the top. And then you get to look over the edge, and then you start going down very quickly. That's potential energy as you go up towards the top, and kinetic energy as you come down. That's another example of a free fall type of ride.
Most of these extreme machines don't use engines or motors after the initial ascent, but there is work involved. The coaster's lift chain exerts a force on the car as it slowly hauls you up that first terrifying hill. Since the displacement of the cars is in the same direction as the force, the coaster stores more and more energy, potential energy, the higher it goes. Then gravity takes over. Potential energy becomes kinetic energy. No matter how many loops, hills, or corkscrews to come, you have all the kinetic energy you need for the ride by the time you reach the bottom of the first hill, provided one thing: that none of the subsequent hills or loops is higher than the first one. To be more precise, the roller coaster can never go higher than what Galileo called the stop height. The 16th century astronomer hypothesized that if you start a marble here, it will always roll to the same height no matter what the shape of the track, as long as there are no resistant forces. If there's friction or air resistance, the same principle applies, but the marble stops at a lower point. If roller coaster engineers didn't obey this principle, these thrill rides would be a real snooze. All hills after the first hill have to be low enough so the roller coaster doesn't stall out. And loops can't go higher than the stop height, or the coaster won't have enough energy to make it all the way around. So all these construction details aside, why does plunging over a hill or speeding along a track give us such a thrill?
Okay, let's go to the reading that we started with. Freefall. Galileo first introduced the concept of freefall. His classic experiments led to the finding that all objects freefall at the same rate, regardless of their mass. Looks like we did that in our little demonstration. According to legend, Galileo dropped balls of different mass from the Leaning Tower of Pisa to help support his ideas. A freely falling body is an object that is moving under the influence of gravity only. These objects have a downward acceleration towards the center of the earth. Newton later took Galileo's ideas about mechanics and formalized them into his laws. Freefall rides are really made up of three distinct parts: the ride to the top, the momentary suspension, and the downward plunge. In the first part of the ride, the force is applied to the car to lift it to the top of the free fall tower. The amount of force that must be applied depends on the mass of the car and its passengers. The force is applied by motors, and there is a built-in safety allowance for variations in the mass of the riders. We're almost done. After a brief period in which the riders are suspended in the air, the car suddenly drops and begins to accelerate towards the ground under the influence of the Earth's gravity. The plunge seems dramatic. Just as Galileo and Newton explained in their theories of free fall, the least massive and most massive riders fall to the Earth the same rate of acceleration. If the riders were allowed to hit the Earth at that speed, coming to a sudden stop at the end of the ride, there would certainly be serious injuries. Ride designers account for this by building in an exit track. The car is attached to this track, which gradually curves towards the ground. A stretch of straight track allows the car to slow down and brake, producing a controlled stop at the bottom. That keeps passengers from getting injured. Okay, that's our reading. Let's go back and take a look at the questions. From what we just heard, which of these graphs would best show what's happening in a free fall ride as the car drops? That's very, very important, as the car drops. Notice again that this is height and this is seconds. Notice that we start at a high point and we move down over time to a lower point. That's graph 1. Graph 2 starts at a higher point, or B, excuse me, starts at a higher point and goes to a lower point, but does it in a very straight way. So that means it's a straight acceleration downward. C graph shows us starting at a low place and ending up at a high place. And finally, D starts us at a low point, takes us to a high point, and then down to a low point. I'll give you a moment to think about that. Okay, if we look at the question, which graph best shows the motion of a car in a free fall ride as the car drops? So that means it's already at the top of the curve. So that knocks out this and this. So our choices are either A or B. If you remember in the reading, they indicated that there's an acceleration and then it slows down to a stop. B doesn't show any slowing down at all, so the correct answer would be A. Okay, let's take a look at number 2. The seats in a car of a free fall ride are replaced with heavier seats. This change requires A, more force to lift the car, less time to stop the car, a lower rate of speed, or a higher rate of speed. The seats in a car of a free fall ride are replaced with heavier seats. The correct answer, well, I'll let you think about it for a moment, would be A. You need more force to lift the car because it's heavier. And finally, let's take a look at what would be our BCR question. Now, I'm not going to write out the answer for you, but notice that it talks about 2 different shaped objects, a round object and a rectangular object. The mass of the rectangular object is greater than the round object. But we already said dropping objects of different mass, like we did with the battery and the highlighter, they hit at the same time, so that shouldn't have an effect. So we can forget about that one. The height dropped in meters, it's the same height, so that's the same, but the time is different. There needs to be something going on here. Let's take a look at the demonstration that I did, and maybe you'll get an idea of one possible error. Here's the battery and the pen. 1, 2, 3. The battery hit first because I released it first. I didn't release them at the same time. That's one possible source of error. Now you can try to come up with a second one. This concludes our 5th grade MSA prep activity for science. Remember, before you take your MSA science test, get a good night's sleep, get plenty of rest, and above all, relax. You'll do well. Thank you for tuning in.